Welcome everyone to today's presentation on input and output system organization. In computer architecture, the central processing unit and main memory are often viewed as the primary engine of computation. But without an effective input and output system, that processing power remains completely isolated from the real world. Over the course of this session, we will examine how computers communicate with external peripheral devices and manage complex data flows across internal system buses. Specifically, we will look at subsystem architecture, peripheral classifications, different modes of data transfer, and hardware/software interrupt handling mechanisms. By understanding how the I/O system manages signal translation, interface timing, and hardware buffering, you will gain a comprehensive. By the end of this presentation, you should have a solid foundation in 5 core areas of I/O architecture. First, you will be able to explain the core I/O subsystem architecture, understanding how controllers, buffers, and interfaces route and manage system data flows. Second, you will learn to classify peripherals into input, output, or bidirectional categories based on data flow directionality. Third, we will compare the 3 major data transfer modes: programmed I/O, interrupt-initiated I/O, and direct memory access, assessing their relative efficiency and CPU impact. Fourth, you will be able to explain how dedicated I/O processors autonomously offload complex data management tasks from the central CPU. Finally, you will learn to differentiate between hardware and software, interrupt-S. At a fundamental structural level, the I/O subsystem serves 2 vital roles within modern computer architectures, acting as a communication channel and performing operations management. As a communication channel, it functions as an efficient, reliable bridge that links high-speed internal processor registers and RAM with diverse external environments. External devices operate across a vast spectrum of speeds, formats, and signal types, from mechanical switches on a keyboard to high-speed optical network links. As an operations manager, the I/O subsystem coordinates all input and output tasks, resolving speed mismatches and preventing low-level peripheral hardware operations from choking the central processor. Without this abstraction layer, the CPU would spend most of its execution clock C. Looking deeper into the subsystem architecture and data flow, we see how external hardware maps directly into internal processor structures. Data generated by physical input devices like a mouse or retrieved from a storage drive moves through an intermediate hardware component called an I/O controller. This controller bridges raw external electrical signals with the internal system bus and main RAM. Within the I/O controller, 3 key components exist: the device controller logic, a local data buffer, and a system interface. The data buffer acts as a high-speed staging area that holds data packets temporarily. This ensures that byte streams coming from slow devices accumulate safely before being transferred across the high-speed system bus in bursts, preventing system bottlenecks. Moving from the internal subsystem to external equipment, peripheral devices are auxiliary hardware units that interact directly with processing memory under the CPU's direction. Peripherals are physically isolated from the main CPU complex and rely on dedicated interface connections to exchange control signals and data streams. In computing, peripherals are functionally categorized into 3 primary types based on their data movement characteristics: input peripherals, output peripherals, and input-output, or bidirectional peripherals. Understanding these classifications helps system designers choose the appropriate controller interfaces, buffer sizes, and bus bandwidths required to handle specific workloads without causing processor stall states. Over the next 3 slides, we will Input peripherals are essential hardware components designed to capture raw, real-world data and translate it into electronic formats suitable for CPU processing and storage. Common input devices include keyboards, which convert tactile key presses into standardized alphanumeric scan codes for software command execution. Pointing devices like mice and trackpads monitor spatial movement and convert physical displacement into digital coordinates on screen. For specialized tasks, graphics tablets use high-precision electromagnetic or capacitive sensors to track stylus movement and pressure levels, allowing artists and engineers to feed detailed design data into the system. In all cases, input peripherals send data inward, moving signals from the physical world into internal memory. Conversely, output peripheral devices convert processed digital data stored in system RAM into formats that humans can perceive or physical mediums can store. The primary visual output device is the computer monitor, which continuously reads frame buffer memory to render real-time graphical user interfaces, video streams, and application windows. Printers take electronic documents and translate raster images or vector commands onto physical paper using ink or toner. Audio speakers and visual projectors convert digital data streams into acoustic waves or large-scale visual projections. These devices operate strictly in an outward direction, consuming process system data to generate visual, acoustic, or physical feedback for the user. In modern computing, many peripherals combine input and output functions into a single bidirectional unit. Input-output or bidirectional peripherals support simultaneous or alternating two-way data transfers between the system and the external environment. Touchscreens are a prime example. They display visual graphics, output, while simultaneously detecting user touch coordinates via capacitive touch grids, input. Interactive displays expand this functionality for collaborative environments, allowing live whiteboarding and real-time interface manipulation. Unified stylus kits combine active digitizers with screen rendering to map tactile pen movements directly onto display outputs in real time. Storage devices like SSDs and network interface cards, NICs, also operate as bidirectional I. To bridge the gap between high-speed internal CPU buses and varied external hardware, system architectures rely on defined interfaces. An interface is a shared boundary that facilitates structured communication between distinct hardware components. Systems utilize two main boundaries: the ultra-fast CPU memory interface and the versatile I/O interface. Strategically placed between the CPU and peripheral devices, the I/O interface handles signal-level translation, serial-to-parallel conversion, and control timing synchronization. By regulating transfer control cycles, the I/O interface ensures that data transfers occur in lockstep, preventing timing misalignments and data corruption when fast processors communicate with slower external peripherals. Now let's examine the three primary modes used to execute data transfers between peripherals and memory, starting with programmed I/O. In programmed I/O, every individual data transfer operation is completely driven and managed by the central processor executing targeted software routines. The CPU executes instructions that explicitly poll the status register of an I/O device to check if it is ready to send or receive data. This requirement for continuous monitoring results in significant CPU overhead, known as busy waiting or polling. Because the processor is locked in a tight loop checking device status flags, it cannot execute other productive tasks, making programmed I/O highly inefficient for high-speed or large-scale data transfers. To eliminate the wasted CPU cycles inherent to polling, hardware designers developed interrupt-initiated I/O. Under this mode, the CPU initiates an I/O command and then immediately returns to executing other primary application tasks. The processor is completely freed from polling peripheral readiness flags. When the external peripheral device finishes preparing its data, it triggers a hardware interrupt signal sent directly to the CPU's interrupt controller. Upon receiving this signal, the CPU temporarily pauses its current program, executes an interrupt service routine, ISR, to perform the data transfer, and then rapidly returns to its previous computational workload, optimizing overall processor utilization. While interrupt-driven I/O frees the CPU from polling, the processor still has to handle byte-by-byte data transfers inside the ISR. For high-throughput devices like NVMe SSDs and gigabit network cards, transferring large blocks of data via interrupts would still overload the CPU. Direct Memory Access, or DMA, solves this by bypassing the CPU entirely during data transfers. A dedicated DMA controller takes control of the memory bus, directly transferring large data blocks between the peripheral and main RAM. The CPU is involved only at the start to configure transfer parameters, and at the end, when the DMA controller issues a single interrupt confirming transfer completion. Taking the concept of offloading a step further leads to the I/O processor, or IOP. An IOP is an independent processing unit specifically designed to manage high-throughput I/O operations, taking the workload entirely off the main CPU. An IOP possesses direct memory access capabilities, combined with the capability to execute its own instruction set stored directly in system memory. These specialized instructions, called I/O control words or commands, allow the IOP to independently format data streams, parse device control protocols, manage error detection routines, and route complex multi-device communication without requiring step-by-step supervision from the main central processing unit. In an IOP-based system architecture, central memory sits at the middle of the system, connected to both the main CPU and one or more IOPs. The system operates under a master-slave arrangement. The main CPU acts as the master, issuing high-level I/O request commands to memory, while the slave IOP fetches and executes these instruction blocks independently. The IOP handles both program-controlled timing with individual external hardware devices and high-speed DMA transfers into shared memory. Once an entire complex multi-step transfer task is complete, the IOP alerts the main CPU via an interrupt, ensuring minimal central processor overhead during intensive throughput operations. Interrupts are essential for modern asynchronous computing. An interrupt is a hardware control mechanism that allows external hardware to alert the processor asynchronously whenever an event requires immediate attention. Instead of making the CPU continuously monitor peripheral flags, devices trigger hardware lines only when they are ready to transfer data or alert the system to status changes. The interrupt system includes prioritization and request resolution logic, allowing the processor to identify which device sent the signal and resolve simultaneous conflicts when multiple devices request service at the exact same clock cycle. Hardware interrupts fall into two primary categories: maskable interrupts and non-maskable interrupts, NMI. Maskable interrupts are standard hardware signals generated by routine devices like keyboards, mice, or disk controllers. The CPU can temporarily mask, delay, or postpone servicing these interrupts if it is currently executing a time-critical, higher-priority task. In contrast, non-maskable interrupts are reserved for critical, unrecoverable system events, such as hardware power loss warnings, chipset memory parity errors, or thermal emergency limits. NMIs bypass standard interrupt masking registers and demand immediate CPU execution to preserve system integrity or safely shut down. In addition to hardware-generated signals, processors respond to software interrupts. Software interrupts are internal, synchronous events generated directly by code instructions running on the CPU core. They generally fall into two categories: intentional software interrupts and exceptions. Intentional software interrupts are triggered using explicit assembly instructions, such as INT instructions or system calls, to safely transition execution from user mode to kernel mode. Exceptions, on the other hand, are unplanned events triggered by invalid hardware operations during program execution, such as attempting to divide a number by 0, encountering an illegal instruction code, or triggering a page fault due to invalid memory access. To wrap up our discussion on input and output system organization, let's review the core concepts. The I/O subsystem bridges central processing units and main memory with external hardware, relying on specialized controllers and buffers to keep data moving smoothly. We categorize peripherals into input, output, and bidirectional devices based on data directionality. We evaluated 3 data transfer modes: programmed I/O, which relies on continuous CPU polling; interrupt-initiated I/O, which uses asynchronous hardware alerts; and DMA, which bypasses the CPU for high-speed memory block transfers. Finally, we looked at how autonomous I/O processors offload complex tasks and examined how hardware interrupts, maskable/NMI, and software interrupts, system calls/exceptions, allow the CPU to. Thank you very much for your time and active attention throughout this lecture. Mastering the mechanics of I/O architecture, from low-level bus timing and buffer management up to high-level interrupt vectors and autonomous coprocessing, is key to understanding modern high-performance system design.